In the first part of this class, we explained you about the models that we use, which are three mainly: YOLO, Masker-CNN, and RT-DETR. So now I will explain you how we evaluate the results of those models, because these models make predictions. They classified certain pattern in the forest that we are interested about. So in this case, for this example, let's say that we are trying to find trees. So when the model predicts a tree, and that is correct, we called it a true positive. So true positive is everything is correct. So then we find another pattern in which the model predicts that there is a tree, but there is no tree. So it's a flower, but the model for some reason makes a mistake and thinks that it's a tree. So this is called false positive. Then there is another case in which the model predicts that there is no tree, but there is actually a tree. So the model missed to find that tree. And this is called false negative. And there is the final one when the model predicted that there is no tree, and this is correct. There is no tree. It's a flower. It's a flower. So these four metrics are used. These four predictions, sorry, are used to evaluate the results of the predictions. So I know that this is very confusing, and I don't pretend that you will learn it in one go, because even until now, it takes some time for me to understand which one is which one. But if you have the more true positives, is better, let's say. The more the true positives you have, the better. So we put all the true positives, false positive, true negatives, false negatives that I explained in the previous slides and create this confusion matrix. The confusion matrix puts all the results together. This is a way to visualize how the model did the predictions and to check where the model made mistakes. For example, this is a study done by one of my students, master students. She was checking how well the model could predict healthy, damaged, and dead trees. And this was the actual number of trees. So if you see the one in the line in the middle, the squares in the middle, all the values that are there are true positive. So true positive means that in the case of healthy, most of the trees were well detected, in the damaged too, and the dead trees were well detected for most of the times. 16 times of the 106 times that there were dead trees, 16 times the model didn't predict them well. And instead of predicting them as dead, 16 of them were predicted as damaged. So these 16 trees are false positives because they're actually dead, but the model predicts them as damaged. So you can play with this matrix and you will find which ones are the true positives, the false positives, the false negatives, and the true negatives. But what we are interested mostly is in the true positives here. Of course, the other values, the higher they get, the lower is the performance of the model. So this has to be taken into account. But if you are sure that you have many true positives, the other values become less important. What I explained about the predictions that the models do are evaluating using these metrics. We have two very important metrics that we need to consider, which is precision and recall. And there is another one, which is the F1, but I will talk about that later in the slide. So let's say that the model makes 6 predictions and the 6 ones are correct. So there is nothing else that the model finds, even though there are 4 more trees. Let's say there are beech trees that they need to find. So in that case, we say there were 6 predictions and the 6 were correct. So the precision is 100%. So there were 4 more predictions that were done, but they were not part of this. They didn't find anything, so they only show here the ones that are found. So there is 10 predictions that are made. 2 are not shown because they didn't find anything. So they are false negatives. And there are 6 that were found and 2 that were wrong, which are false positives. So this 1, 2, 3, 4, 5, 6 predictions that are true positive, they are correctly identified. There were 2 incorrectly identified, these 2, and there were 2 more, four more that were not found. So in that case, we have that the precision has decreased because now you have 8 from 8 predictions, 6 were correct. So 75% of them are correct. So if you can see here, the precision doesn't care about the false negatives. So the false negatives are not part of the evaluation in the precision, but in the recall they are. So in the recall, they want to know how many of them were found and how many of them were not found, not how many were mistaken. It's not evaluated here. So you have 10 trees that are supposed to be found, but the model only found 6. So your recall is 60%. So now we go to the F1 score, which is the overall evaluation of the model. And we have that in the first case, when the precision was 100 and the recall was 60%, the overall prediction of the model is 75%, which is not so high. But when you have, in the second case, when your precision is 75% and your recall is 60%, then the model performance is lower. So if you don't find trees that are supposed to be there, then your recall becomes lower. But if you make mistakes identifying trees, your precision becomes lower. And these two are put together to evaluate the overall performance of the model. This is again something that is not easy to understand in one go, but if you start using it, you will realize where is the weak point of your model. That does it identify too many trees incorrectly, or does it miss many of the trees that were supposed to be found and they were not found? Now, for a better understanding of everything that I have been explaining, I would like to show you 2 study cases that we have done in my laboratory. Both of them are PhD students that are under my supervision. The first one is about the evaluation of temporal trends in forest health status using precise remote sensing and deep learning. And the second one is about the automatic tree species identification in a cold temperate natural broadleaf mixed forest using high resolution UAV imagery and Mascar CNN, which is one of the models I explained before. So the first study case is in Zhao Mountains. As probably you all know, this is an area that has been severely damaged by bark beetle infestation, by a bark beetle infestation, and has destroyed most of the forest and has caused several health issues. So in this study, we have the same workflow as before. We bring the drone, we collect images, we prepare the orthomosaics. The orthomosaics are in the orthomosaics, the trees under different health condition are annotated They are extracted for training data sets that will be used for YOLO models, and then the YOLO model is applied. The annotation data, I mentioned that you can do it by a human expert, by someone who knows about this. But nowadays, there are also softwares that do annotations for you. But of course, they have to be supervised. Someone has to make sure that the annotations that the software is doing are correct or not. And one of these softwares is MakeSense.ai, which some of my students use. But what I always hear from them is that they have to check if the results are correct or not. This is the way I mentioned before. We look at the white pixels, which are usually the pixels that have no leaves, the branches that have no leaves, because the branch, when loses the needles or leaves, as you want to call it, they become this very gray, whitish gray color that at the naked eye, it looks like white. So here we have this shape, the green color of the parts of the tree that are foliated, and the white. So this is just an explanation of how we classify the different health status of trees. And this student in particular, who is Tobias from Germany, he worked quite a lot with pixels manipulation, and he was able to classify trees' health in a more mathematical manner. So he had different health categories, including fallen trees and including objects that were always in the image. People sometimes, the roadway sometimes. And it was interesting because until 2021, we have the different categories of health of standing trees. But from 2022, we had some trees that were fallen, and they were obvious in the orthomosaics that we made from that year. We also found some interesting characteristic of trees that were standing, for example, in 2021, fell down in 2022, starting losing the branches, the leaves, and by 2024, the tree had practically disappeared. It had been covered by shrubs or by sasa or by other vegetation. So the trees that fell down basically disappear from the images. So here he list up all the annotations that he has for healthy, light damage, medium damage, heavy damage, dead, fallen, artificial objects, and humans. And this is the train data set and the validation data set. So he divides the percentage of data for training and validation, and finally the data set that it will be used for testing the model. So this is his confusion matrix. So all the variables that all the true positives, false positive, false negatives that you see here are considered in this matrix. As you can see here, the model was not perfect, I would say. It performed well, but we expect that in the future it will perform better. You find 66 trees that were categorized as healthy and were actually healthy. Then the model predicted that these 23 trees were healthy, but actually they were light damage, and one was medium damage. So there is a bit of confusion between the healthy, light damage, and medium damage, especially between light damage and health. Then the model predicts uh, light damage quite well, sometimes mixed up between healthy and medium damage, which is understandable. And then medium damage, heavy damage, and dead are more or less well predicted. And the fallen trees are all identified correctly, but the model also missed some trees. So these are the false negatives because they are there, but the model didn't identify them, which are very few, actually. I was quite surprised. It was very few. So in that sense, the recall is not so bad, but I can assume that the precision will not be so high, and that will make the overall evaluation lower than we were expecting. Then you have the metrics. So this is already the evaluation of the model. Tobias did something that I found quite interesting. He tried to use all the categories. So divide the different health categories, especially the damaged, between three categories, which was the light damage, medium damage, heavy damage, but also include the dead, the fallen, and the healthy. So if you see the F1 score, the dead is very well identified. So you have 94.1%, almost 100. So the dead is easy to identify. I was quite surprised with the fallen because the fallen is also easy to identify, but he only got 76.9%, which is not bad, but it's not so good. The healthy was also good, and the light damage, medium damage, and damage were oscillated between 68.8 to 66.4. It's not bad results, but here you can see that the medium damage, the F1 score was lower because there were many false negatives. There were very few false positives, but the false negatives decreased the accuracy or the whole accuracy of the model. So then Toby decided, okay, what happens if we don't divide the damage? We just call them damage trees and we don't divide them anymore between light, medium, and heavy. So his model increased considerably, and he also grouped dead trees and fallen trees because in the end both of them are dead, and he called them decay. So in this case, you have three parameters only: healthy, damage, and decay, or three classes, sorry, or three categories. And he found out that the precision went incredibly high. So now there is no mixed up between the categories, and identified the trees quite precisely. There were very few false positives, and even in the recall, the false negatives decreased considerably. So now you have an F1 score, which is the overall evaluation of the model, with very high values, especially for the damage and the decay. So this model is quite good. You can see in the figure how the model is evaluating single trees. So this is damaged one, or the category light damage, with 48% probability of prediction, or healthy with 72, healthy with 78, healthy with 0.85. So the higher the value, the more confidence the model has that the prediction is correct. So these models were, in my opinion, very, very good. They have a very good prediction for the health condition of fir trees in Zhao. And this paper was accepted, and the results were quite good. Intersection of union means the percentage of tree canopy that is framed in the square that you see in the images. So how much of the canopy is actually trapped within this these frames. So it's quite high. Again, for dead decaying trees, for dead trees and damaged trees is quite good. And for healthy is not so bad either. I mean, considering that this is a natural forest and sometimes the trees are overlapped with each other, then it's a good result. If the forest is a very sparse forest where trees are very well separated, then it's no problem. The model, the intersection of union will work perfectly. But in this case, the results are quite good. The second case is a study that we did in uh, in the Yamagata University Research Forest. This is a forest that we have used for many, many years, and we have conducted many studies here. We have published a lot using different methodologies, but in this particular study, we used deep learning. But for that, as I explained before, we first collected UAV images quite intensively for the year 24, 25, and we are collecting again now in 26. So we collect images in different seasons because we want to use the phenology of trees for easier identification. We try to collect as many images as possible. Sometimes the weather doesn't help so much. If it is sunny and you have too much shades, this is not good for the image. So some of the orthomosaics that we made here, we didn't use them in the end in the model because the data was not so reliable. So this is part of the experience. You go many times, and if the weather is perfect, you're lucky, but that will not always be the case. So this is the results of the tree species identification. The total area was 20.5 hectares. The range went from 550 meters to 750 meters. And these are the main species that we found here. Beech is the dominant. At the top, you find birch. There's some small percentage of cedar, chestnut, cypress that I am not sure why they're there, but there is a very small percentage of larch. Magnolia is more present. Maple is more present, but they have a smaller size. There are some Mizuki, oak is very important. Pine, also very few, cherry, walnut, and some other trees that are not so significant. So in this area, we counted all the trees. This information by itself is already very important. We are not using any deep learning for this. And from my point of view as a forest researcher, this is the data that I want. This is the real data. These are trees that we have identified with drone images. And regardless of the success of the deep learning model, this is already hard data. And this already explains very well the distribution of tree species in a natural mixed forest in Japan in a temperate region. So if the model can reproduce this that has been done by humans, it will be fantastic. Fantastic. But if the model takes still some years to do it, you can already do this kind of a study, and this will give a very good understanding of what how are tree species distributed in this type of forest. Vladislav, who is the gentleman here on the right, is a very good student, very meticulous with his analysis, and he decided to not trust fully the classification or the annotation done in the orthomosaic, but he created his own methodology using small UAVs and QGIS field software to verify if the trees were being identified correctly. And he went with this iPad that you see here, the remote controller, and went on top of each tree and got as closer as possible to identify the leaf shape. So this leaf shape was gave the final confirmation that this tree is a beech and this tree is an oak tree. So this was very good, excellent work. So he was able to correct because the manual annotation, this is what you get from the orthomosaic, and this is what you get after the correction. So there was a lot to correct in beech trees. There was nothing to correct in birch, so they are very easy to identify. Cypress, a little bit, but anyway, there were very few. Large trees, only very few corrections. Magnolia also. Maple needed lots of corrections. Oak also needed almost half of the corrections. So this gives you an idea that some trees are easy to identify only in the orthomosaic, and some trees are very difficult to identify in the orthomosaic, and you need an extra validation method. The best validation method is that you go to the forest, look at the tree, and verify it. But in 20 hectares of very rough terrain, of very close forest, of not accessible places, it's almost impossible. So this methodology that Vladislav has developed of UAP and QGIS is really good. It's the first time somebody has used it. So I hope in the future many people will use it. And he also is using now in his new study. So this is a Mascar CNN that he used for the model and that I explained before. So he has this area that I explained, that I showed you before, and he divided it in training and testing area. So the training is the yellow and the testing is the bluish square that you see in the middle, because they have most of the species that are at the bottom and at the top of the forest are found here. So this is his training data that you see here, beech, oak, and then the testing data. So he tries to see if the model Masker CNN can find it or not. In the end, just to give you a warning, he tried to find all the species, but the model didn't work very well. So he focused on the 4 main species that we were interested to find in this forest. And those 4 species are beech, larch, oak, and magnolia. So all the letter A, all the images with the letter A are the natural image. No annotation, nothing. The second one, all the B's, are the annotations that humans did. So you see here a larch, an oak, a magnolia, a beech. So, and the C images, C1, C2, C3, are the masks and the detection that the model did. So if you can see just these images, you will realize that actually the model worked really well. Not so much in the counting of the trees, but very well in the identification of the species. The counting of the trees is very difficult because sometimes it's difficult to separate one tree from the other. But the masks are very well done. So the model worked really well. I was quite surprised and quite satisfied to see these results because the model worked actually very well. So this is the matrix of the 4 species. The values are not higher because in the case of the precision, there are um, false predictions, of course. So trees that were not found, that were categorized as one species, was not categorized as the other. But you have also to think that this is not one tree species. These values are for the four classes, for beech, for larch, for oak, and magnolia. And the recall is telling us that there were many trees that were not found, but actually they were found, but were there two trees, where there were two trees, it was classified as one. So it means that you missed one, but actually they were identified, but not as divided as two, but as only one. So this is something that we are working on now. We want to increase the amount of data to see if the model can learn better. But this is a very good initial result. For this forest that is so complex, to get this type of results is really remarkable. And I can say, based on this is the overall value. But if you see one by one, larch has 65, beech has 57, magnolia was 55, and oak has the poorest performance. This is something that still we cannot explain very well, why oak is the performance is so bad. But we think that maybe increasing the number of data, and this is what we are doing this year, could have could improve the results of the model. So I want to leave you with this last slide, which is about deep learning models and forestry. And I don't want to give you the wrong impression that deep learning models are already perfect and working without any trouble in forestry. I think it's the contrary. And I explain it here. So at present, the degree of accuracy of these models depend not only in the model itself, but also in the type of forest. Now, the constant and rapid improvement of computer capabilities, software, and expertise will increase the accuracy with time. So that's why I always mention that the work that we are doing now is more pioneer work. That in 5-10 years' time, the models that we have created will be much, much better, but the data that we have will be used for that improvement. So we are creating these huge databases that in the future will probably be used by somebody else. So in this last decade, deep learning model applications around the globe constitute the pioneer work in this new field. So for anyone that is trying to work on this field, I will recommend you to learn well about forest, because it's not only about computer science. You need to understand some processes inside the forest, but also to work on your skills of computer science, because this will help you quite a lot. I, in particular, have very good partnership with a professor in the Faculty of Science. He is supervising all the models that we used. But I realized recently also that some of my students who did not have so much computer skills at the beginning, they have started to develop their own skills, because they are young and they see that in the future it will be better if they understand not only forest, but also how the deep learning models really work. And in the future, I am completely sure that the deep learning models will replace human classification, human expertise to classify different characteristics in the forest. I have no doubt about it, but I want you to take into account that classifying is one thing and the interpretation of the data is another thing. So if it doesn't matter how much you can classify them, if you are not able to use this data to interpret processes in the forest, uh, you will not be taking advantage of this data as forest researcher. Okay, well, I leave you with this. Thank you very much for your attention. I hope you like this video, and if you have any question, you know where to find me. My homepage is online, so you can see it anytime you want. All right, see you until the next time.